Hi, everyone. Thank you for attending this last talk of the day. As you can see, this session is a postmortem on implementing autoplay in Unreal Engine 4. To preface, as you can probably tell, I can't talk about the project directly, other than it's a AAA action RPG for the PlayStation 4 and Xbox One. It might be a little obvious what the project is, but I have a little request, which is if you were to make any social media posts, to not directly associate this talk with the project itself. And yes, Unreal Engine 4 will be referred to as UE4. For development of this project, we used UE 4.17.2. First, the contents of this talk. There are three major topics that I will go over. To start off, a brief self-introduction, followed by some information on the automation work I have done on this project. Next, I'll talk about the autoplay system. And finally, I will go over the results of using said system. I've made the talk such that it should be understandable by non-programmers, but there's a lot to go over, and there might not be enough time for a Q&A, so feel free to approach me afterwards if you do have questions. Anyway, let me briefly introduce myself. My name is David Sim Wei Lun, but please call me David. I was born in Singapore and joined Square Enix in June of 2017. Before then, I had worked as a programmer in Singapore and in America. For this project, I mainly worked as an automation programmer, but aside from automation, I've also done work related to engine, tools, player controls, and enemy combat. As far as automation work goes, in addition to autoplay, I worked on automating a handful of other systems. Broadly speaking, these systems can be broken up into three categories. The first type involves updating data through the editor. This is done using UE4's automated tests feature. Most of you probably know about it by now, especially if you attended Jessica Baker's talk yesterday. But just in case, you can access this feature through UE4's session front-end window under the Automation tab. Using this feature, various unit tests can be run on the editor, the engine, the game, and so on. The automated tests I implemented were mainly for the environment team. This included tests that automatically updated existing asset types like HLOD, as well as custom data assets related to permanent resident assets and texture loading. In general, the tests would reference some existing data and either import or update the target data. For example, when updating the HLOD data, the test would open and reference the target map. After updating, it then submits the data to the version control system, or VCS, that we use. Moving on, the next type of automation is for quality assurance. This typically involves profiling systems, but can include other in-game systems, such as a system to play all cutscenes. It is quite a broad topic, but the general flow of automation for each system is quite similar. In general, each system has their own special launch arguments that our continuous integration system specifies. Then, in order to figure out what to load and in what order, the launch system reads that information from a text file. Typically, the system is hooked into various events using blueprint nodes and controls the game using debug commands, while the actual profiling is being carried out. As far as the commands and nodes go, we used both pre-existing and custom-made ones. While profiling, results are usually simultaneously uploaded to a database and output to a CSV file. Once the profiling is done, our CI system gathers the results and performs its own upload to a file server before finally sending a notification email out. To be precise, there are three kinds of QA-related systems that we automated. The first includes a system that measures the performance of actors one at a time in a blank map. There were about 100 actors, including players, party members, and enemies. While it was only for enemies, there was another system that profiled roughly 450 attacks. The second category involves profiling various maps. Initially, it was only 12 maps, but that eventually expanded into various locations within each map itself. And that grew from like 50 to about 720 locations in total. The last category wasn't so much used for profiling than it was for creating cutscene-related data. One such system had to play approximately 270 cutscenes in succession. Regarding automation of this kind, the bottleneck had to do with the scope of the data, especially when it came to the large number of locations and cutscenes. While we wanted to run these systems daily, a single run would often take more than 24 hours. This made it impossible to run it within a day, especially after including the downtime from error handling and starting up and cleaning up. In the end, however, we came to the solution of being able to run it daily by splitting the work across 2 to 4 dev kits. Another bottleneck was that if a crash, an error, or for some other reason the system were to fail halfway, it wouldn't be able to resume profiling the remaining data by itself. To solve that is the third type of automation, which involves external tools. While this type isn't just launcher tools per se, launcher tools were used for handling potential errors that may occur while running our profiling systems, especially at the scope that we were running them at. The tool itself isn't that complex, however. It essentially uses our target platform's API to launch the game and monitor its output log. If an error is detected, or if the time limit set is exceeded, the tool will restart the dev kit and have the profiling system resume where it left off. Other tools under this type include a tool to analyze code log warnings, one to organize the profiling results, and another that merges data for PGO, which is a type of optimization. Since these tools are external, they aren't directly related to UE4, and you could say CI/CD services also fall under this category. Usually, all 3 categories of a system were used together as a set. Typically, the external tools manage the in-game systems, which in turn generates various data. The editor then uses this data to update various assets. It is using this flow of automation that I automated the generation of PGO and cutscene-related data. As you might have already guessed, autoplay can be considered to be an in-game system. Before I go into details of the system itself, let me briefly go over autoplay as a concept. As the name implies, autoplay is a system that can play through the game automatically. I think there are various ways to go about this, of which I'll give 3 fairly simple examples. The first example is by replicating the user's input exactly. This is probably one of the simplest methods, and so the more complicated the game gets, the harder it might get to use it efficiently. Since the input is replicated at predetermined timings, it is easy for the replication to fall out of alignment with what is actually happening in the game, especially if any lag or loading time fluctuations occur. For those same reasons, this method isn't very compatible with the non-deterministic parts of a game. And for those unfamiliar with what that term is, I'll get back to the meaning of determinism and non-determinism later in this talk. The second example is by using AI, or in particularly, randomly moving through a space by referencing in-game data, such as a nav mesh. As opposed to progressing through a game in a linear fashion, it is a method that is well-suited towards exploring an area thoroughly to check for things such as collision issues or performance. The third example is by using some other kind of data to move through the game's world on a fixed path. Some refer to this as golden path. For example, representing the data as coordinates, and while moving between coordinates, performing certain actions at a fixed time. By the way, as far as resources go, I had drawn inspiration from Bayonetta 2's autoplay system and the Yakuza series' auto test system. I referenced various resources, including those that I have up on the slide. In a sense, this version of autoplay is a hybrid of all 3 examples. However, the third example is probably the closest to what the system is at its core. In other words, it is a system that primarily uses coordinates to move along a fixed path, but also uses input replication and game data to support its progression through the game. I'll show a longer version of this at the end of the talk, but this is what the system looks like in action. Yep, so to be more specific, what the system does is read the coordinates from a text data file and move the player along a fixed path of those coordinates without the use of AI. While moving between coordinates, the system replicates user input as well as executes commands, both of which are specified within the text data as well. When the data alone is not enough to overcome things like special situations or mini-games, the system then relies on in-game data to advance. That's the basic idea behind the autoplay system. But as for how I decided on the system's design, I'll explain that by going over the 5 objectives we came up with, while also going into further detail about the actual systems themselves. And by the way, the objectives are numbered, but it's just so that they will be easier to follow and they don't reflect the actual priority. So to start off, autoplay's, one of autoplay's objective is to save time on playthroughs. That is simply because, due to the scope of this project, a single playthrough is very time-consuming. Towards the end of development, a single run typically took over 10 hours. This seemed like a huge waste and an inefficient use of time, especially when key developers were involved. Admittedly, I also have my own personal interest in such a system since the time I was in America. And as mentioned earlier, I was also inspired by other titles that implemented similar systems. 3 systems were implemented to accomplish this objective: a recorder system for creating the data, the autoplay system itself for running the data created by the recorder, and a playlist system for running multiple data consecutively. As I was making use of my experience with the other automation systems on this project, the foundation of the autoplay systems bear multiple similarities with them. For example, all these systems require specific launch arguments and text data. They also attach to the same callbacks and control the game using more or less the same debug commands. In addition, they are all updated around the same time, which is near the end of the game instance's tick. As long as the arguments and data are valid, these systems can be run on any dev kit, which includes both PS4 and Xbox One. However, one tiny difference is that the autoplay systems are mainly run using the command line. Moving on to the next objective, which is that the data can be created and run by anybody. This is mainly because it wasn't realistic to handle the data creation all by myself, given the scope of the project. It also seemed more cost-efficient to build the system in a way where I wasn't limiting the potential users of the system. In the end, we went with having a 3 to 4 person team, nicknamed the data team, to handle data creation and support. It is thanks to this team that we were able to finish making the data. For data used with PGO data generation, however, we did have another person handling it. It is based on this objective that the recorder system was implemented. In order to keep the bar of entry low, plain text was used for the data format. We did consider using behavior trees and AI controllers instead, but decided against it since that limited the number of potential users. What the recorder mainly does is record gamepad input. It also has a debug input mode, where instead of recording input, it records player coordinates or changes the recorder's settings based on specific button combinations. As shown on the slide, the recorder outputs coordinates in this format, line by line. If any buttons were pressed prior to recording the coordinates, it will also output the timings and buttons in the order that they were pressed. The coordinates and timings are written as numerical values, and to make parsing easier, a single character is used to represent each button. There were also various commands that can be specified instead of button input. Commands can do a wide variety of things, such as making the player wait a specified amount of time, or skip to the next set of coordinates on receiving a cutscene notification, and so on. The more elaborate the command, the longer they get, and aren't usually limited to a single character. The downside is that most of these commands have to be input into the text data by hand. Therefore, the typical workflow for creating the data is to first create a foundation to work with using the recorder. Then, through trial and error from running the data, perform adjustments or add commands by hand till the data is complete. Going back to the topic of objectives, another is to handle deterministic sections with data. Conversely, it is also to handle non-deterministic sections with code. Just in case, let me briefly go over what I mean by deterministic and non-deterministic. A process can be said to be deterministic if, given the same parameters, it will always produce the same results. On the other hand, a non-deterministic process's results cannot be predicted accurately, even with the exact same parameters each time. With a deterministic game, we could, in a sense, recreate any given frame within a game as long as we know the parameters of that frame. Chess and certain fighting games can be said to be deterministic, as well as the previous talk about RTS games. In my opinion, the more interconnected action there is in a game and the more random elements there are at a given time, the closer the game gets to becoming non-deterministic. As you may imagine, while there are deterministic sections in this project, there are a lot of non-deterministic sections as well. So the use of an input replication system was simply not enough to achieve our goal of being able to play through the whole game automatically. We relied as much as possible on data, particularly for deterministic things like linear movement and fixed timing input. But for non-deterministic things like battles or mini-games, it was better to handle that with code and let the autoplay system take the reins. Moving on to the fourth objective. It is to keep the system's design and features simple. This is merely because there wasn't much development time left in the project. One compromise that was made based on this, though admittedly not a very desirable one, was that it was okay for the autoplay system to take up some performance. Based on this objective, priority was given to tasks that could be more easily or efficiently solved. Harder tasks were temporarily solved using debug commands and were eventually dealt with properly. For example, we would skip minigames by warping the player to the point after they were completed, or use a kill-all command to win battles. About the actual details of the autoplay system itself, I'll start with going over how movement is done. At its core, it is a system centered around coordinates-based movement. That is to say, it moves the player along a fixed path. I do think, however, that an autoplay system that uses AI for random pathing could be a great complement to this system. You've already caught a glimpse of it earlier, but this is what it looks like when the system is moving the player. As you can see, it is simply moving the player in a straight line in between coordinates. And while moving between points, the system performs other inputs at specific timings. Regarding the implementation for carrying out input, it is done through the player controller to make it as close to the code path of actual user input. The camera direction and the direction of the destination relative to the player are used to figure out which direction the left stick should be tilted towards. The calculation itself is actually not very complicated, and some of you probably know about it, but it's probably easier to understand using a top-down perspective. If we rotate our view such that the camera's direction is aligned with the vertical axis of a 2D plane, the direction of the destination will match the direction in which we should tilt the left stick. To put it another way, by figuring out the angle between those two directions, we can rotate a 2D up vector by that same amount to get our desired results. Movement is relatively easy, but handling the various states of autoplay is somewhat complicated. While in the beginning, there were only 5 states, which wasn't complex at all. In the end, it grew to a total of 31 states. From handling various menus to all kinds of mini games and game modes, having to deal with them individually made the process complicated. This is especially because certain states have the possibility of being interrupted by other states. So a lot of care was required to handle each potential transition properly. Also, while debug commands were used to temporarily skip the non-deterministic parts of the game, they were eventually handled properly through the autoplay system by looking up information held in the relevant managers or pawns. For example, if the enemy manager class showed that there was at least one enemy, the autoplay system would switch to its battle state. Or if the UI manager class showed that it is displaying the title screen, the autoplay system would initiate the necessary button inputs to start a new game. One other thing this game had a lot of is what you would call special situations. Basically anything that is not part of the core gameplay loop, including mini-games or special gameplay modes. While the way these were handled are by and large the same, there are roughly 3 types of these situations. The first type involves using a specific ability of the players in order to progress further in the game. For example, pointing the camera at a specific location, then activating a certain ability in order to progress to said location. For handling such cases, using the information stored in the player controller or pawn was sufficient. The second type involves either controlling an actor that isn't the main player character or navigating specific UI. There's a possibility that the controls may be different in such cases, but usually it is enough to simply switch to using the relevant controller or pawn. The last type involves minigames. Typically, player control is retained, but the objectives are varied in nature, such as collecting a large number of moving targets or having to press a randomly selected button. For such cases, they are handled by searching for the target using either a pawn or actor iterator, and by checking for obstacles using line traces. The autoplay system also has what is known as a bug detection and tag feature. The bug detection feature checks for 3 things: whether the player's Z coordinates is near the kill Z plane, whether the travel time between destinations has exceeded 5 minutes, and whether the total time passed since the data was run has exceeded a certain amount of time. This is to check for any game-related bugs, such as the collision settings of the environment. Another thing this checks for, however, is whether there are any issues with the autoplay data itself. This is because the game was changing at a high frequency, and there were a lot of non-deterministic sections. So it was often the case that the system would get stuck at various points of the game, at least until development had slowed down. Regardless of which bug it is, if any of the 3 checks fail, the system would output to an error log, take a screenshot, and optionally create a dump, so as to make investigating the cause of the failure easier. In order for the autoplay system to continue executing the data with little interruption, after outputting everything, the system would warp the player to the current destination and target the next destination. As for the tag feature, it is used to associate a debug jump point with a destination. If the system sees a tag associated with the destination, it will use the tag's jump point instead of warping the player. The tag feature is also used for executing the data from its middle, though that isn't related to the bug detection feature itself. Even if the system were to get stuck in dozens of places, using the bug detection and tag feature, we were typically able to resume data execution. Overall, this allowed us to maintain coverage of most of the game's playthrough. In a sense, battle is another feature of the autoplay system. Its default behavior is quite simple. We have a list of enemies stored in our enemy manager class, which we target in order. And when I say target, I don't even mean locking onto the enemy. The player simply makes a beeline to the target, and once within a certain distance, would spam the attack button. There aren't any path calculations or obstacle detection, So it is possible to get into situations where the player is unable to carry out a single attack. For example, if the player were to get stuck on an environment, or if the enemy is larger than the range used for determining whether to attack. To counteract this, after a certain amount of time passes, the system would use a debug command that kills all enemies. To prevent game overs from occurring, another debug command is used to make the player invincible. In addition to this really simple battle mode, an expanded version was made mainly for PGO. This version makes more use of all the features available in battle. By making use of UI and player information, this version would lock onto enemies, switch targets on the fly, and execute any of the abilities available to the player at random. By using this mode, we applied it to performance-intensive battles and player abilities to generate PGO data in order to perform various optimizations. There are two other features of the autoplay system. The loop system is, as its name implies, when execution of the data has finished, the system loops back to the beginning of the data and repeats it. The retry feature is also kind of straightforward. During battle, it will set the player's HP to 1 and deliberately control the player in a way to cause a game over. It then selects the various options available in the game over screen and resumes data execution from the previous destination. The intent of this feature was to test the many checkpoints in the game that were used after a game over. Unfortunately, this is one of the only features that was unused due to a lack of time in updating the autoplay data to be compatible. One final thing about the autoplay system is how it is launched. First off, as mentioned before, specific launch arguments are required to enable the system. Once enabled, it can be activated through the command line using the autoplay keyword followed by the name of the data file. Various flags can also be specified after the file name. For example, how many times to loop the data, whether cutscenes should be skipped, or how the system behaves during battle. The final system implemented, which is a level above autoplay, is the list system. In a sense, this system ties together all 4 objectives mentioned thus far. As you can guess from its name, the list system's primary feature is to execute autoplay data consecutively, kind of like a music playlist. I should also mention that we organized the autoplay data on a per world basis, so each file represented a playthrough of a single world. The list data itself also uses a plain text file, which, as shown on the slide, lists the data files in the desired order of execution. The autoplay flags can also be specified separately for each data file, which will only apply to that file during execution. Similar to the autoplay system itself, the list system is also activated using the command line and its corresponding keyword, followed by the file name. This system can also be started in the middle or looped. In addition, you can specify autoplay flags on the autoplay list command line, which would override the flags within the list file. With regards to the loading of the data and list files, it might be worth mentioning that it is all done using pre-existing fFile helper and fstring functions. Last but not least is the 5th objective, which is simply to use the build types that have debug features. The test build was made the primary target since it retained certain debug features while being the closest to the release build. Whenever we needed additional debug features or information, we will use the debug build instead. While we did consider using the shipping build, it didn't have much debug features, or if any at all, and it seemed risky to enable something like autoplay on it, so we decided against it in the end. I'll next talk about the results of autoplay, but before that, let me briefly go over its implementation costs and how it was actually operated. It took roughly 2 months in total to implement all 3 systems from scratch. It took an additional month for the systems to be considered feature complete, which includes things like being able to properly handle various special situations and the expanded battle mode. However, what isn't included in that time frame is the additional support costs for autoplay. What I am including in said cost are things like having to update the data, fulfilling various requests, and fixing bugs. Including the efforts of the data team, this lasted all the way till the end of development, which I would like to emphasize as being rather costly. Regarding the data files, in the end, there were 20 of them in total. This includes files for each world and files for progressing in between the worlds. There were 400 total revisions across all the files, so each file had taken roughly 20 revisions. And based on the graph shown, it took on average 6 months of support per data file. It's a little hard to tell based on numbers alone, but most of the support costs came from finding issues with the data on a daily basis and fixing those issues. However, I should also mention that both the data team and I had other responsibilities, so it wasn't like we were working only on autoplay all the time. Next is the operational workflow of autoplay. As you probably expect, data-related tasks were mainly handled by the data team, while system-related tasks were handled by me. First, the data team creates the necessary autoplay data. Then, both the data team and QA runs the data each night before heading home. The kits that the data was run on include both PS4 and Xbox One. I also run the data on my kits whenever they aren't being used for other tasks. Then, on the next day, everyone uploads the results to a file server. The data team then checks those results and reports any findings through chat and/or email. If there were any issues, we would first verify whether it is an actual game bug by contacting the developers related to that section of the game and attempt to reproduce the bug by hand. If it appears to be an actual game bug, we would create a bug ticket, which QA would then verify. If they are able to reproduce it, we would then escalate the ticket accordingly. If it isn't a game bug, it is likely an autoplay bug. We would then verify if it is data related or not. If it is, it becomes a data team task. Otherwise, especially for things that can't be fixed without code changes, it will become a system task on my end. We also have some basic rules regarding submitting data to our version control system. Basically, we only allow autoplay data used for playthroughs and PGO to be submitted. There are a whole bunch of other smaller data, which I created for things like testing bosses or reproducing crashers, but those were never submitted. All of the data, submitted or not, were placed in the game data debug folder, since it would never be included in the release build. This directory is also where we place the text data used by the other automation systems. Moving on to the results of autoplay, I'll start off with how it benefited the project. There were 3 main areas where autoplay was used. One area is, as you can imagine, QA related. As expected, we saw the most usage out of playthroughs, but it also saw usage in check-in environments and the behavior of bosses. The sound team also made use of it for audio-related checks. Another area involves checks over an extended period of time. This mainly has to do with bug reproduction and verifying bug fixes, especially the kind that have such low reproducibility that it took an entire night or even days to verify. Towards the end of development, autoplay was also used for investigating memory leaks. The last area has to do with optimization. In addition to being used to generate PGO data, autoplay was also used for observing the game's memory, load time, and texture pool. By tracking those elements of the game, we were able to discover other types of memory leaks and irregularities with certain cutscenes. Relative to the initial goal of having a system that can carry out playthroughs, we saw much wider usage than expected, which is awesome. Even though there were only a few users per team, there were about 8 teams in total that used autoplay, which was more than we had expected. Furthermore, by running autoplay every day, we were able to discover or confirm multiple hard-to-reproduce crashes. Also, this is a very rough calculation and might not mean much, but in terms of the total amount of time that autoplay was used, which excludes any estimated downtime from bugs or breakages, it amounts to approximately 900 workdays across all the teams. Of course, as useful as the system may have turned out to be, that doesn't mean it doesn't have any shortcomings. One such issue was its support cost. It is precisely because of the system's simple design that it became tricky to deal with new aspects of the game that were added later in development. I feel that led to a significant amount of tech debt. And because of the high frequency in which the game was updated, it was only towards the end of development that we started seeing greater stability in the autoplay data. Editing the autoplay data isn't easy either. The system's documentation is really long due to the number of features and minute details it has. And there are a ton of commands that can be used, which made it challenging even for me to edit the data that was doing complex things. There are also a lot of possible flags, so if you're using some complicated settings, entering all of that into the command line could become quite tedious. Furthermore, since autoplay does a bunch of atypical things, such as running various debug commands depending on the situation, even if we discovered what appears to be a bug, it wasn't always obvious whether it was actually a bug or not. To be fair, however, this issue was somewhat alleviated after we started using capture cards to record everything, since we could better analyze the circumstances that led to the potential bug. One other thing, which isn't so much an issue, but rather an unfortunate side effect, is that because the system did take up some performance, we didn't really use it for profiling. Most of this performance came from carrying out various checks on the game every frame on the main thread. While this was avoided as much as possible by relying on attaching to callbacks instead, due to the potentially complicated nature of state transitions and non-deterministic sections, there were a lot of times where checking every frame couldn't be avoided. We, of course, would like to tackle all of these issues over time. For reducing the high support costs, I think putting more emphasis on planning out the system would help. While it might be fine to simply increase the dependency of autoplay's data on the game's actual data, that may simply be shifting the burden of responsibility to the people responsible for said game data. So I think this is quite a delicate balancing act. It more or less boils down to a question of who should shoulder the cost of supporting the data and system, which should be decided on carefully early on. That is pretty much what we did for this project, and is how we decided on the data team members. For reducing the difficulty in editing data, I think abstracting the obtuse parts away with an editor tool and reworking the data format would help. Similarly, for reducing the time taken to input stuff on the command line, switching to a GUI should not only help, but also make it easier to control the system. To be honest, I've yet to come up with a decent solution for bug differentiation, other than continuing the usage of capture cards and possibly improving our log output. As for using the system for profiling, I'm hoping to switch to a multi-threaded design or possibly converting the system into an external tool. And this is a really rough compilation, but there are plenty of other improvements that we are also looking into, which range from expanding the system to further automating its operational workflow. So to summarize this postmortem, through the implementation of 3 systems based on 5 objectives, we were able to fully automate playing through the main story of the game. These goals were fulfilled through collaboration with the data team, resulting in much wider usage than expected. While the support cost was high, we saw high returns as well, which may actually be greater than our conservative estimates. there's also plenty of room for improvement, and by maintaining the momentum behind such a system across multiple projects, I believe autoplay can become an indispensable system for the development of any AAA title. And I'll just let this run to its end, which is almost there. And that's pretty much it. Thank you for your time today. Thank you for listening. I think